All right, guys. So now we're going to look at RLC series circuits. So as the name can suggest, this is a circuit with the R for resistance, L for the inductance, C for the capacitance. So we have all of those three circuit elements now in series together connected to the function generator. Okay. So when we have this type of, let's say, a circuit with those three connected in series like this, then in a way what we have here is type of system that resembles damped harmonic oscillations, because if you have inductor and a capacitor, like we learned last time, those two can give you sort of like oscillatory motion in a circuit, right, for the energy. Um, so we can have an oscillation in the circuit, but because now we have also a resistor that can then create this dump, let's say, effect on the system. That means there will be a dump due to this resistance. That means energy, let's say, in a circuit will be eventually dissipated as heat because of the resistance. Now, so on the right side we have a dumped, basically oscillator, mechanical oscillator, where the spring system, the spring is pulled to the right to some maximum distance from equilibrium, then let go. All right, so in absence of friction, the system will then oscillate back and forth relative to this plus minus A, where A is the amplitude. And then energy will go back and forth between kinetic and potential energies. But as soon as you have um, friction, friction then will work like basically a dissipative device, or sort of like, let's say, in our circuit, similar to that, where the friction then will dissipate kinetic and basically kinetic and potential, mainly mechanical energy, into heat. And the oscillation eventually will come to rest. That means if we're looking at position, let's say, in this case, like x as a function of time, starting from some maximum displacement, then our graph will be plus A here, starting from plus A. It will go, but never even reach minus A on the other side if there is a friction, and eventually will slow down and dissipate. So this is basically we call damped harmonic motion. And it's a very good analogy here because the resistor here in a RLC circuit basically plays the same role. All right. So what we have here in this RLC circuit, so we have a function generator that give us delta V max, delta V as equals to delta V max sine omega t. That means this is just basically what we get from a function generator. So we can write this delta V here is delta V max, then sine omega t. So we get that from a function generator. But then what we have here is this current here. Can get rid of here. So then the current will be, again, time varying, and it will be I max sine omega t minus phi. Okay, so we have a current that's going to be from this function generator. And one thing we know here is that because all those three circuit elements in series, same current will then technically go through each one. Okay, so same current will have to go through each one. All right, so let's look at in terms of some of those properties. All right, so we have a circuit element in series, current everywhere must be the same at any instant. All right, so then the current at all points in series has the same amplitude and phase. That means if you're looking at the current to the resistor, current to the inductor, current to the capacitor, well, they're the same current. All right, so then voltage across each element has different amplitude and phase. Now that's something different. That means current here, IR is equals to IC is equals to IL, but then the voltages are not the same. Okay, so now this phasor diagram allows us to see how the voltages are different for each of those circuit elements. So on the left side, here we have first the voltage across the resistor. That means potential difference across the resistor. And you can see that we can, basically present it as pointing in a positive X direction. Why? Because remember, in a resistor, voltage and current always in phase. That means taking the current to be just, in a positive x direction, and because the same current for all of them, we're going to see that each of those phase diagrams have exactly same current pointing in the same direction, and Imax is exactly the same for all of them. But we know that if that's the case, it means that if the current is always in a positive x direction, the voltage only in the same positive x direction for the resistor, because only in the resistor voltage is in phase with the current. That means here we can see that voltage and current, both of them basically pointing in a positive x direction, both of them are in phase. For the inductor, then what we can see here is the inductor voltage is ahead of the current voltage by 90 degrees. That voltage across inductor leads current by 90 degrees. And we have seen this already, right? In a previous, like, let's say, slide, we derived this. That we just said that current is lagging by 90 degrees. That means if you have the voltage, if you have the current that, sort of like, let's say, always going to be in a positive x direction, that means voltage across inductor always will be then 90 degrees ahead of it, or pi over 2. And then if we go to the capacitor, okay, for the capacitor, it's other way around, right? So then the voltage, lags by 90 degrees, or the current is ahead by 90 degrees. So then this will be then the voltage. Remember, these phasors are vectors. And in a way, what we're doing here is we're saying that now for the voltage, we have three different vectors, right? Delta VR is in a positive x direction, delta VL is in the positive y direction, delta VC in a negative y direction, and also the size of those vectors give you information about the magnitude, right? So the magnitude of that vector, which one is more, which one is less, and you can see from here that delta VL, which is the voltage across the inductor, is greater than the voltage across the capacitor. Okay, that means those three things, basically must be satisfied if we have RLC circuit in series. Okay, now in terms of then what we can do from here is understand that we have now three voltage values. Delta VR, which is the voltage across resistor, is equals to Imax times R. Remember, so technically, if I'm writing this in terms of Vmax or delta Vmax, right, then sine omega t. Remember, so this is basically same as writing as Imax, right, times R. So that's the maximum voltage. Then sine omega t. That means this is basically my voltage across the resistor. Then the voltage across the inductor then will be delta VL, which is the amplitude, right? So let me put like, or if you want, like a Vmax, and then cosine omega t. So, which means that in this case, I can write it in terms of Imax times the reactance, inductive reactance, then times sine of omega t plus phi. Okay. Then if I'm writing in terms of delta VC, then this will be then in terms of negative Vmax, then cosine omega t, and then this can be written as in terms of Imax times inductive capacitive reactance, then sine of omega t minus phi. Okay, now we have those three voltages, and in a way, then what I have here is, if I want to find, let's say, then get the, so like, let's say the sum of all those voltages to get, in terms of the total voltage, right? So because what I have here is the sum of delta V's, right, here is equals to then instantaneous, right? This I mean, like let's say sum of V max. Okay, so this is equals to instantaneous voltage. Right, voltage. Okay, but one thing we have here is this. If I want to add them together, right? So I'm not going to be able to because there, you can see, right? they have different phase, right? So they have a phase difference, and relative to their current. So then we cannot just add them directly. Okay, so doing the delta VR plus delta VL plus delta VC, in this case we cannot just do that, because it's just like, when you remember, right? So if you're trying to add horizontal vector to the vertical vector, you can't, because they're different directions. So the similar idea is here. That's because, like, let's say they have a different relationship with respect to their current. For the VR, it's in phase with the current. What the VL is, out of phase with the current, and VC is out of phase, like differently, like let's say lagging compared to being ahead. But the idea here is that we cannot pretty much add them together. And this is where this phasor diagram comes into help. So phasor diagrams then allows us to look at in terms of what we have for the um, voltage across the resistor, voltage across the inductor, and voltage across the capacitor. And if we can represent them as vectors like this in one graph, you can see right here, if I can put them, all three of them as vectors together, then I can see that I have a horizontal vector, VR, and I have two vertical vectors for the inductor and a capacitor. And I can combine those vertical ones, right? Delta VL and delta VC can be combined. And then I have this, which is basically the delta VL minus delta VC, because delta VC is in the opposite direction of delta VL, and we're treating them like vectors. So then in a way you can say that, both of them, if we add the vertical forces, vertical vectors together, so this is basically their difference pretty much. And this vector represents that. But now I have this vector, which is basically the net vertical contribution, and this one here is the horizontal. Then using the parallelogram method, right, we can see that this will be then delta V max. That means we can get the maximum amplitude of the resultant, using this graphical method. That means it makes our calculation, right, much simpler, because of the fact that we can represent them as vectors. All right, so let's see then what we have. So basically what I have here is, I have delta VR. Let's say that's basically in this case, I can see, right, that's the adjacent part of it, right? That's the adjacent part of it. And then I have, this is basically my, the vertical part of it. So in order to get the delta V max, I can treat this as a triangle, where this is delta VR, this is delta V max, and this will be then delta VL minus delta VC. Then I can say that to find then the side, right, which is delta V max. So delta V max, I can just use the Pythagorean theorem. Delta V max square is equals to delta VR square plus delta VL minus delta VC squared. Okay, so I can basically do that. And then if I take the square root of both sides, then I have then delta V max is equals to square root of delta VR plus delta VL minus delta VC. All right, so let's rewrite this here again. That means delta V max, that's the amplitude, right? The equals the square root of then delta VR in this case, right? So this is basically, as phasors, we're adding their amplitudes, right? Delta VR square, then plus delta VL square, sorry, delta VL minus delta VC squared. So basically putting it like this. All right, so here I can rewrite this one as delta VR is basically nothing but, representing that in terms of Ohm's law. So then it's I max times the resistance square plus then delta VL will be I max times then inductive reactance minus I max times the capacitive reactance squared. Okay, so basically write it like this. And then one thing I can see that each term has I max basically, I max squared, right? So I can factor it out. Now, if I factor out I max, then what I will get here is this delta V max is equals to then I max. I can factor out completely out of the square root. And inside the square root, basically I end up with R squared plus X sub L minus X sub C squared. Okay. Now, this equation is analogous to the Ohm's law. Okay. Where, what we have here is that delta V is proportional to the current, and then there's a, kind of proportionality factor, which is the, resistance in the circuit. And that's basically what we have. So over here, this quantity that we have in a parenthesis, including, right, this is basically represents the resistance, right, opposition to current for the RLC circuits. And that means that basically what we call impedance. So impedance is square root of R squared plus X sub L minus X sub C squared. And we defined that to be Z, capital Z. And obviously it has units, of ohms, because that's basically represents opposition, to current. All right. That means this is being then the impedance equation, where it's, you can see, right, because we have resistor, capacitor, and an inductor in the circuit, the overall opposition to the current is not just in terms of resistance, but because of remember, the unique sort of, like, let's say, relationship that inductor and capacitor have to the current, in a way that basically they act like, opposing to the current, sort of like a devices. The impedance basically takes into account not only resistance but also reactances. All right, so then I can rewrite this equation as delta V max is equals to then I max times then impedance, or finally rewrite this, in terms of the maximum current, which will be then delta V max divided by then the impedance. Okay. So that's kind of like, let's say, the equivalent to the Ohm's law, right, for the AC circuits. Okay. Now, impedance basically depends on four things. If you look at the equation, so resistance is one thing that impedance depends on, and it depends on inductance, capacitance, but also, if you remember, right, those reactances, both of them were frequency dependent. Remember, XL was equals to omega L, and XC is equals to 1 over omega C. That means, in a way, I can rewrite this impedance as square root of R squared plus then omega L minus 1 over omega C squared. So we can basically also rewrite it in terms of this, because we can see from here is then there are four things basically that affects the impedance: resistance, inductance, capacitance, and the frequency. Okay. All right, so this basically give us, if you come back to the triangle, so we had delta VR, and this was delta VL minus delta VC. Now, one thing is missing. This allows us to calculate delta V max. One thing is missing was then the direction phi, and then that's another thing that we can calculate by using that right triangle, which, if I'm representing this as delta V L minus delta VC, which has become my opposite side. Delta VR is my adjacent side. Then I can use then tangent of theta, right? So tangent of phi is equals to basically the opposite over adjacent, where then my opposite is pretty much delta VL minus delta VC. My adjacent is delta VR. And then I can use that to calculate the phi, which is you take the inverse tangent of that. So you can see, right, the inverse tangent is delta VL minus delta VC divided by delta VR. And again, if I rewrite all of those potential differences in terms of the Ohm's law, right? The current times the reactance for the delta VL and delta VCs, and the current times resistance for the delta VR, then you can see that all three have current. You can, cancel all the current and technically have an equation for the, uh, this angle, right? Um, as in terms of just the difference between reactances divided by then the resistance. So that's basically your argument inside the tangent, inverse tangent. Okay. Now, from here we have this. When x sub L is greater than x sub C, so you're dealing with, in this case, dealing with the high frequencies, because high frequencies represent um, much higher uh, inductive reactance than the capacitive reactance. So in a way, we can kind of see that from this diagram. So let me kind of do this here. So think like this. So this is basically my frequency. So then this is my, opposition to the current. This is basically the reactances and the resistance. Remember, x sub L is equals to omega L. That means x sub L, represented with the blue line here, increases with the frequency. That means x sub L is, as a reactance, is larger at higher frequencies. X sub C is equal to then 1 over omega C, which means that capacitive reactance is higher at the lower frequencies. Let's use the red for that. So then this is basically this is X sub C. And that means, at the lower frequencies, X sub C is larger than X sub L, which is this one is a blue line over here, right? So you can see, right, when the frequency is low, let's say somewhere in this region, you have much higher, capacitive reactance than inductive reactance at the lower frequencies. But at the higher frequencies, then what you get here is the opposite, right? At the higher frequencies, then again, this is X sub L and this is X sub C, which means that over here, when X sub L greater than X sub C, you get basically higher frequencies, then phase angle is positive. Why? Because this difference here is positive, okay? And the current lags applied voltage. So the circuit is more inductive than capacitive, okay? That means when you are somewhere in this region, then you have a positive phase angle and your circuit basically is more inductive than capacitive, and current, lags applied voltage. That means applied voltage is ahead. Okay. Now, let's then look at over here when we have X sub L less than X sub C. Obviously, then this is a lower frequencies, right? At lower omega. So basically somewhere over here in this region. And then what we have here is you can see that over here, then X sub L is less than X sub C, which means that phase angle is negative because X sub L minus X sub C going to give you a negative number. Okay. Now in this case, then the current leads applied voltage. So the circuit is more capacitive than inductive. Okay. By the way, if I have to then do a diagram or let's say a plot for the for the resistance, well, that will be something like this, right? So that will be something like this, where the resistance is never changes because it's not a frequency dependent device. Okay. All right, so now there's another very important let's say sort of configuration or a frequency of interest. That frequency is right here when X sub L and X sub C cross. When they cross, that means at that frequency, let's call this omega naught, at that frequency, X sub L is equals to X sub C. Okay. Which means then X sub L minus X sub C is equals to 0. So the phase angle is 0 because if here you're doing 0 over R, that's tangent of 0, which then basically gives you phase angle of 0. Which means that your circuit basically completely ignores the reactances from inductor and the capacitor. That means it's purely resistive. That means the impedance Z is which is equal to square root of R squared plus x sub L minus x sub C square. Well, those two cancel each other. That means Z is equal to square root of R square or R. That means your impedance only, purely resistive. Okay. That means this happens when your reactances are exactly the same. Okay. So that is known, we're going to see, right, as a resonance frequency. Right, we'll talk about resonance frequency a little bit later. Here, let's talk about power in an AC circuit. Okay. So now, one thing we're going to do here is we're going to look at in terms of our circuit again. So we have a RLC circuit where we have a resistor, inductor, and a capacitor. That means what we're gonna have is that we're gonna look at in terms of a power, right, delivered to those devices. Now, one thing we had here is the power in a DC circuit, if you remember, was just the current times voltage, right? P equals I times V. Well, this is, let's say, DC. So power is equals to I times V. That means the power across resistor would have been basically written like this, right? Current through the resistor times voltage of the resistor and things like that. Now, if we talk about then for the RLC circuit, well, things like this. So same way, then it would have been power of the inductor, right? So this would have been in terms of the current through the inductor times voltage of the inductor, which, we could have write in terms of then, L times di dt. And then power for the capacitor would have been, the current through the, capacitor then times voltage of the capacitor, where then the voltage would have been Q over C and so on and so forth. But, let's say right now what we have here is for the AC circuit, then we're going to look at in terms of instantaneous power delivered by AC source to a circuit, which is then going to be equal to the product of current and applied voltage. Okay, remember, all the current is the same in this case, right? So IR, IL, IC, they're all the same, so we can just write some I. And then delta V will be then the voltage delivered by the power source, right, our function generator. Then for the RLC circuit, R, RL, R, RLC, okay, LRC, RLC, doesn't really matter. They're all in series. So then the AC circuit, then what we have here is this. So the power is equals to I delta V. And remember, in a way, what we're doing here is we're looking at instantaneous power, right? So because, it's very difficult to look at in terms of, we talked about, right? So either you look at average power or the maximum power or instantaneous power, because power changes constantly. Voltage and current, they're all sinusoidal. That means, what you have here is, just every instant something, the value is different. That's why what we have here is when you look at the current, it's a current, time varying current times time varying voltage. So the current here is I max times then sine of omega t minus phi. That's basically my current in a RLC circuit. Then times voltage. And then the voltage will be delta V max, then sine omega t. Remember, so for the RLC circuit, current here is 90 degrees out of phase with the voltage. All right, so if I calculate this, then I end up with P is equals to I max sine of omega t, then sine of omega t minus phi. All right, so and actually, I've got delta V max. Also, technically can go there, but it's part of the equation. Okay. Now, from here, what we see is that basically this result is a relatively complicated function of time, and it's not necessarily helpful or practical for us to use. So what we can, try to get and derive here is the average power, as I mentioned, right? So in terms of, let's say, when you look at the power in the AC circuit, just like everything else is time varying, and even this is instantaneous time, instantaneous power, and even this, a relatively complicated function. So what we do here is, let's say then try to get the average, power. Just like, it's always easier to work with the RMS values than, let's say, the voltage and the current. Same thing is here. So it's much easier for us to work with the, let's say, average power equation. All right, so let's look at then what is the average power in a, in AC circuit. All right, so what we do here is we take sine omega t minus phi, and we can rewrite this. So sine omega t minus phi, then this is equals to, using one of those Greek, the trig identities. So it's sine omega t cosine phi. So minus then cosine omega t sine phi. Okay. Then if you plug in back, so P is equals to I max delta V max. And then for, sine omega t, so you have then sine omega t, then plug in sine omega t cosine phi minus cosine omega t sine phi. So then here we'll have I max delta V max. So we take this, multiply by sine omega t cosine phi. So this will give us sine square omega t cosine phi. Then minus um, I max delta V max. Then sine omega t times negative cosine omega t sine phi. So, well, the negative already is there. So it becomes then sine omega t cosine omega t, then sine phi. All right, so we end up with this equation. Okay. Now, if we look at then the time average of P over one or more cycles, we can see that the I max, delta V max, phi, and omega are all going to be constant, assuming that we're looking at, in terms of one cycle and two cycles, three cycles, and so on and so forth. Those quantities will be basically constant. So then the time average of the first term on the right of the, of the equal sign is basically involves the average value of sine square omega t, which is basically, one half. The time average of the second term on the right side of the, equal sign is then identically zero, because sine omega t cosine omega t. So if you combine those together, right, is equals to one half sine 2 omega t, and average value of sine 2 omega t is then 0. All right. That means this will be then simplified to P average is equals to 1 half I max delta V max. And anyway, the only surviving term here is basically cosine of phi. And that's what we write down. So that's basically in terms of my the average power. Okay. So then sometimes it is convenient to express the average power in terms of the RMS current and RMS voltages. Remember, so these are now in terms of maximum values. But if I then rewrite this in terms of RMS values, then average power is equals to IRMS delta VRMS, then times cosine of phi. That means that's the average power in terms of those RMS values. All right, so then again, let's write this down over here. P average is equals to IRMS times delta VRMS, then times cosine of phi. That's, how we're going to write the average power for the RLC circuits. Then what we have here is this, a cosine of phi. This is then defined as a power factor. This is defined as a power factor. All right, so now what we can look at here is in terms of, we can see that in terms of to get a maximum voltage across the resistor. So then we can look at it in terms of delta VR is equals to delta V max cosine of phi. Okay. And remember, the delta VR is always equals to I max times the resistance. That means from here we can rearrange and solve for the cosine of phi for the power factor, which is equals to then I max then times the resistance over delta V max ratio. Okay. So now from here, I can rewrite this as I max over delta V max, okay, times the resistance. And then we can identify this technically uh, inverse of the impedance. Because remember, so the impedance here is delta V max equals I max times the impedance. So then if I rewrite this in terms of um, basically take the inverse of both sides and divide by I max. So then here's a Z, right? Then delta V max over I max is the impedance. Inverse of that basically is inverse of impedance. That means this becomes R over then impedance. Okay. So this is basically the equation for the power factor. Okay. Then we can express the average average power as going back. So it's IRMS times delta V RMS times power factor, but I can now represent that as a R over the impedance, resistance over impedance. Then from here, we can write it down in terms of IRMS, then times delta V RMS over the impedance times R. And just like this one suggests, right? VR, V max over I max or VRMS over IRMS, ZRMS, right? So that can give us basically the RMS, current. That means always, in terms of VRMS is equal to an IRMS times the impedance. So if I divide both sides by impedance, then I get IRMS, which means I already have one IRMS here, and another one is right coming from here. Then the average power here is then equals to IRMS squared times then the resistance. Okay, that means that's basically in terms of finding the average power. So that means you can use this as equation to calculate average power. But same way, we can always write this in terms of the current times voltage, but using the RMS values. So IRMS times delta V RMS. So basically, just like in a case of the let's say DC circuits, right? In this case, we assume like let's say if the power factor equals to 1, this basically gives you the most efficient the circuit. So when here cosine of phi is equals to 1 unity, then you basically get the most out of your circuit, right? So in this case, let's say phi equals to 0, which means that cosine of phi equals to 1. That means sort of like phi equals to 0, cosine phi equals 1. This is when your load is purely resistive, remember? Because when we calculated tangent of phi, this was x sub L minus x sub C divided by R. Um, that means in this case, if I take, those two b equals to same and so their difference is 0, then meant that phi equals 0 and your load is purely resistive. Okay. That means you, in a way, you get the maximum resistance in your circuit out of that. All right. So, and in this case, then no power losses associated with the ideal capacitors or ideal inductors. They're pretty much, you know, basically kind of like, let's say, removed as a device from a circuit. Like they pretty much acting like a extension of a circuit, and the only thing you think of, like let's say in your circuit right now, is there's a function generator and a resistor, and energy that was stored in a capacitor, and basically temporarily stored in a capacitor and in the inductor, and there is no energy transformed to the uh, resistor, right, as internal energy. All right, so here's in terms of what we have. Those are the energies associated with the inductor, and that's a power equation in terms of average power. So IRMS delta V RMS values. So from here, those energy basically is the maximum energy stored in the, you can write it's kind of like max, the maximum energy stored in the inductor. So then when the current in the inductor reaches maximum value, in this case, you can say that, the all the, other type of energy is basically now converted into magnetic energy. So when the current begins to decrease in circuit, then stored energy in inductor returns to the source as inductor attempts to maintain current in the circuit. And then that's the equation for the power, average power. This is power delivered by AC source to any circuit, and you can see that it depends on the phase. Okay, so that's why when you have phi equals 0, this is when um, reactances are equal to one another, and your system is purely resistive. If phi is not, phi is equals not equals to 0, it's less than 0. um, Sorry, if basically the cosine of phi is less than 1 in this case, right? Then you calculate the power that is basically depends on this, on the phase, depending on what phase you have. And in this picture here, then what we have is a factory where the uses large motors in machines, so generators or transformers, and they have large inductive load. uh, because you can see, right, those are basically, a lot of solenoids, basically, so a lot of wires running together. So then to deliver the greater power to such devices without using excessively high voltages, what they do, they introduce a capacitance in their circuit to shift phase. Because then if you have a capacitance where then the reactances from the capacitance matches the reactances of the, let's say, inductors, then basically you get maximum effectiveness, right? So then you can get, like, let's say, cosine of phi is equals to then 1 in that case. All right, so one thing I mentioned that we're going to come back here was that the resonance frequency. Remember, resonance frequency, again, is basically the when the system exhibits maximum response when driven at its natural frequency. Okay, so that's basically what we have, a resonance. So in a series RLC circuit, so electrical oscillating system with, with natural, natural frequency. That means everything, generally oscillates with some kind of what we call natural frequency. All right, so then what you have then a driving frequency. Okay, so now imagine, right, driving circuit with a sinusoidal voltage, expect resonant phenomenon. That's basically if the driving frequency matches the natural frequency of your system, then what you get here is, you can say that your system seems to be in resonance. That means this is when the driving frequency is such that RMS current in the circuit has the maximum value. Okay, so we're going to see the diagram. So in terms of, resonance frequency, basically is when the driving frequency matches natural frequency, and this pretty much occurs when you have reactances that, equal to one another. So remember this impedance equation for RMS current. Now you can see, right, so in terms of, like, when is it the maximum? Well, it's maximum basically when x sub L minus x sub C, right? Basically they match each other. And at that instant, so you basically, uh, this is, x sub L minus x sub C, right? So when this is equals to 0, then you can see, right, in your equation, you have delta V RMS divided by, square root of R squared plus XL minus x sub C. And in this case, this is equals to 0. So um, your delta VRMS is just basically divided by just a resistor, which means that you only have a resistor in the circuit that opposes the current, instead of also getting help from the reactances. All right, so we have a plot of RMS current um, versus angular frequency, and let me scroll here. So this is the diagram for um, the if you're plotting the current versus the angular frequency. So one thing we can see here is you have three different curves, and so you have curve 1, 2, and 3. Okay, So that means this is, if we look at then again, equation for the RMS current, this was equal to then delta V divided by the impedance. So let's say delta V over the impedance, or delta V um, RMS, then divide by square root of R squared plus X sub L minus X sub C squared. Okay. So now what I have here is at the frequency where X sub L minus X sub C equals to 0. That means, the frequency when that happens, we call it, resonant frequency. So it's some omega naught. That means my current here, IRMS, is equal to then delta V RMS over then basic sort of R squared plus 0, right? That means this is just basically delta V RMS over R. That means in this case, we can look at in terms of the dependence of this only on current, on the resistance. That means the current right now only depends on the resistance at this particular, frequency. Well, when R is equal to 0, it's just basically 1 over 0, just basically means the current here is, infinitely high, right? That means, RMS, the RMS value becomes infinite, at this resonance frequency when R equals 0, because already reactances cancel each other. Then if there's no resistance, it basically blows up and becomes infinitely high. Obviously, this doesn't really happen because there is no such thing as no resistance. There's always a level of resistance in the wires. But obviously we can look at in terms of, for example, some, cases where there, you go from 10 ohm resistance to 5 ohm resistance or to 3.5, which means that, lower the resistance, higher the current, right? You can see, right, that RMS current has, basically already, uh, becomes like, let's say, the higher, reaches maximum value at this particular frequency, because, the impedance is the lowest, right? So impedance is basically thing like this. So it's Z square equals R square plus X sub L minus X sub C square. That means, no, regardless what this is, which one is bigger, X sub L or X sub C, it's their difference is squared. That means this can always give you some number, and then you have R squared plus that number. That means impedance is always going to be large when the circuit gets contribution from the reactances. But when this is 0, that means, your impedance is the lowest, during the entire, range of frequencies. Well, when your impedance, remember, impedance is the resistance of RLC circuit. Where impedance is the lowest, that means the current is the maximum. Okay, that means at this frequency you get the lowest impedance, but that means, you get, maximum current in your circuit during the entire range of the frequencies. So then we can say that as the resistance decreases, the current basically increases. That means, the current reaches its maximum value at the resonance frequency omega naught. And obviously, when the resistance is 0, it's going to be like infinitely, let's say the peak, well, we, pretty much can reach infinity. But as I mentioned, right, there's technically no such thing. So, and there's always some resistance which limits the value of the current to some always finite value. All right, so then we can write down the average power in terms of then delta V RMS squared, R times omega square, and divide by then R square omega square plus L, L square over omega square minus omega naught square. Now, in terms of, where this equation coming from, well, remember the average power was equals to IRMS square times resistance, but also delta V RMS square over the impedance square times resistance, because that's what this guy here is, right? That means IRMS is, voltage over the impedance ratio. So we end up with that. So then if I kind of like, write down everything, let's say in this case, what the impedance is, right? Kind of like factoring out, some of those terms. So then we can eventually basically end up with this equation. where then we can write x sub L is equals to omega times L. Then x sub C is 1 over omega times C. Then one of the things we have here is basically this, right? So um, at the resonance frequency, right, when x sub L minus x sub C equals 0, that means, omega L is equals to 1 over omega times C. In this case, then, if you cross multiply, so then I get omega square is equals to 1 over LC, or omega equals square root of 1 over LC. This then known as the resonance frequency. That means it shows that the resonance frequency when omega is omega naught. So then you can just basically replace this with those equations, right? So in terms of, like, let's say you can see, right, you have omega and you have omega naught, kind of like, where you pretty much, factor out, the C here, you're writing omega squared is equals to 1 over LC. So then the C is equals to 1 over, omega naught times L, and then factor out, basically substitute this for the capacitor over there. And you can see, right, this is the equation then for the average power in terms of the RMS voltage, resistance, inductance, but instead of the capacitance, so basically we introduce, this resonance frequency. Okay, that means this shows that the average power, maximum, and has value of delta V RMS over the resistance, which means that, when those two equals to one another, right? When those two equal, that means that omega is equals to omega naught, which is, you get the resonance frequency. This whole thing goes to 0. Okay, and then this omegas cancel out from there, and this R cancel out with that. Then you just get the delta, delta V RMS square over R. Okay. Okay, so then this graph then shows the average power versus frequency, and again you get that, the resonance frequency, right? Which shows that as the resistance decreases, curve becomes sharper in the vicinity of resonance frequency. Okay, that means, the average power basically, also, uh, depends on, in terms of here, depends on the resistance here, right? And delta VR, and basically at omega naught you get maximum power, maximum average power. Okay. So one thing we have here is what we call quality factor. Here Q. This Q is basically written as omega naught over delta omega, the ratio of the resonance frequency over the width of the curve, right? Delta V. So the delta V basically, you can say delta V width of the curve is where P average equals 1/2 the maximum value, or half power points. And with the half power points has a value of delta V, so delta omega equals R over L. So if it goes to R over L, that means we can replace delta omega with the ratio of R over L. Then we can get this quality factor as, resonant frequency times inductor divided by the resistance. Okay. So that's the equation for the quality factor. All right, so let's look at some examples here. So we have a circuit that consists of an ideal AC generator, 20 microfarad capacitor, and an 80 ohm resistor, all connected in series. The output of the generator has a peak EMF of 20 volts, and the armature of the generator rotates at 400 radians per second. So let's find the power factor, the RMS current, and the average power supplied by the generator. Okay. Now, what we have here is, so we're given the value of the capacitor and inductor, and sorry, the capacitor and the resistor. And what we have here is we can basically have a resistance and a capacitor together in series, and then we have a function generator that has a peak EMF, which is this is the Vmax, so 20 volts, and then capacitance is 20 microfarad, and the resistance is then 80 ohms. Okay. Now it says that the generator rotates at 400 radians per second. Okay, so 400 radians per second is basically given the frequency, right? Omega is equals to 400 radians per second. All right, so then one thing we can do here is we can like say, okay, so here's a circuit. All right, so this is R and this is the C. And the diagram for this can be like that. Okay. So we can look at it in terms of this is R and this is X sub L minus X sub C, and this is being the impedance. Okay. And then from here we can say that for part A, it's asking for the power factor. Remember, what is power factor? Is cosine of phi, and this is was equals to R over Z. Now the Z is the impedance, which is square root of R squared plus X sub L minus X sub C squared. But for our particular circuit, X sub L is equals to 0. We don't have an inductor. And in that case, then our cosine of phi is then equals to then R divided by square root of R squared plus, well, it's negative XC squared, but just basically because you're squaring that, so X sub C squared. Okay. That means cosine of phi is equals to R divided by square root of R squared plus, well, this is the capacitive reactance, which means it's 1 over omega C squared. Then we have resistance value, capacitance value, and the frequency. We can just plug in and calculate it. So this is equals to 80 ohms divided by square root of 80 ohms squared, then plus 1 over 400 for the frequency times 20 times 10 to the negative 6 farad for the capacitance. Well, plug in everything, calculate, we're going to get 0.54. Remember, the power factor is always going to be a number between 0 and 1. Okay, and it's dimensionless. It has no units. So it will allow you to kind of calculate a number and verify if you did it correct or not. If I got like that, let's say here 55, that means I did something wrong. So that kind of can give you a way of verifying your answer. Okay. Second part says, what is then the RMS current? Okay, now for the RMS current, then so I have IRMS is equals to, remember, so this is then VRMS divided by the impedance. Okay, but I don't have VRMS, I have Vmax, so I have to be careful here. But I know if I have Vmax, I can easily calculate RMS value from that, which because it's a Vmax divided by square root of 2, that's basically my RMS value. And then this divided by impedance. Okay, so let's calculate that. That means it's Vmax, then square root of 2 times impedance. Then my Vmax here is 20 volts. Then divide by square root of 2. Then times, impedance, which is, 80 ohms squared plus 1 over 400 times 20 times 10 to the negative 6 farad squared. I forgot to square that over there, so it should be squared. Well, while plugging this, we get 95 milliamps. There you go. So that's basically my answer for the maximum RMS current. Part C says, what is the average power supplied by the generator? Well, so let's say this is B, this was A. For the part C, then what I have average power. There are a number of ways we can calculate, but remember the easiest one is IRMS squared times the resistance, because I have 95 times 10 to the negative 3 amps squared times 80 ohms. Plug in this, we're going to get 0.73 watts. That's our average power. Another example, you have series RLC circuit that has an inductance of 10 millihenry and the capacitance of 2 microfarad. We're also given a resistance of 5 ohms and is driven by an AC voltage source that has a peak EMF of 100 volt. All right, so we're given now an RLC circuit, the resistor, inductor, capacitor connected to a function generator. Okay. And we pretty much given all their values, right? L is 10 millihenry, resistance is 5 ohms, capacitance is 2 microfarad. All right, so then we also given Vmax as 100 volts. For part A, we want to find what is the resonance frequency. Okay, so let's look at in terms of resonance frequency. All right, so for resonance frequency, for part A, it's simple enough because resonance frequency is equal to then 1 over square root of LC. Okay, remember, this is basically because x sub L minus x sub C equals 0 at the resonance frequency. That means then x sub L is equals to x sub C, which is omega times L equals 1 over omega C, and then rearrange and we get this. So then I can calculate 1 over square root of, so 10 millihenry, so 0.001 Henry, then times then, I think I put like 1 Henry over there like that. So 1 0, so that's 10 Henry, 10 millihenry. Then the capacitor is so 2 times 10 to the negative 6 farad. Okay, so we calculate, so we will get 7.1 times 10 to the 3 radians per second. That's my resonance frequency. Okay, part B. What is the root mean square current at resonance? Okay, that means RMS current. What is IRMS? Well, this is VRMS divided by the, remember, so this is resonance frequency, so impedance, but we have that, so at this frequency, at resonance frequency, Z is equal to just R. Okay, so I can say just VRMS over R. So VRMS though is again not given, so but I can say this is just Vmax over square root of 2 and times R. That means it's 100 volts divided by square root of 2 times 5 ohms. Okay, plug in this, we can calculate this to be 14 amps. All right, part C. What is the capacitive and inductive reactances? Well, again, simple enough. X sub L is equals to omega L. Omega is then we just calculated 7.1 times 10 to the 3 radians per second times omega, which is 0.010 Henry. That's going to give us 80 ohms. Okay. All right, so 80 ohms. Okay, roughly speaking. Then let's calculate the. All right, sorry guys, so I made a mistake here because I didn't read it carefully. It says when the frequency is 800 radians per second, then find the capacitive and that means, we come back here because this is no longer at the resonance frequency. And we can see that it's not resonance frequency because reactance is not going to be equal to one another. See, at this frequency, when I calculate x sub L and x sub C, which you can, right, plug it into these equations and calculate them, they will be exactly the same value. But here we have 8,000 radians per second. So here I get 80 ohms. Then I have to then separately calculate x sub C because now it's going to be different because it's not a resonance frequency. So 1 over 8,000 times 2 times 10 to the negative 6 farad. So then here you get 63 ohms. Okay. All right. So that means, I have then capacitance, a capacitive reactance to be less than inductive reactance. That means we can assume that any frequency larger than resonance frequency, inductive reactance will be higher. Any frequency lower than resonance frequency, inductive, the capacitive reactance will be higher. That's also another thing you can use to verify, because you can see, right, our resonant frequency is 7,100 and this is 8,000, higher than the resonant frequency. Last one is part D. Let's see what it's asking. Well, not the last one. So part D says impedance. Well, for impedance, again, I can use Z. This is assuming at 8,000, 8,000, like let's say radians per second, uh, the frequency. So then this is equals to then R square plus X sub L minus X sub C square. That means this is square root of 5 square plus then 80 minus 63 square. Okay, so then if I plug in and calculate, so we should get 18 ohms. Okay. This is basically the total resistance in the circuit due to all those three things together. All right, so the next part E was asking to find the root mean square current for this frequency and then the phase angle for part F. So let's do that. So IRMS for this particular frequency will be then VRMS over the impedance. And again, we can assume that driving, driving like voltage is still the same peak voltage, which is 100 volt over square root of 2 times impedance, but this guy's impedance is 18 ohms. So then we can calculate 3.9 amps. Okay. And finally, part F, where then calculating this time not the power factor, which is cosine of phi, but the phase angle. That means uh, you know let's say phi here, you can write like this, and this is then you can take into tangent, inverse tangent of um, x sub L minus x sub C divided by resistance. So inverse tangent of um, 80 minus 63 divided by then 5 ohms, right? And this is going to give us then 74 degrees. So then this will be the phase angle for that.